Hello, friends. I hope you're all feeling fit and healthy. Today, we'll be diving into Chapter 3 on NMR. Let's begin by exploring the concept of spin-spin splitting. In NMR spectroscopy, spin-spin splitting or J coupling is the interaction between magnetic fields of neighboring, non-equivalent nuclei, causing a nucleus's signal to split into multiple peaks. These groups of hydrogens appear as multiplets, named singlet, doublet, triplet, etc., based on the number of peaks, due to interactions with neighboring hydrogens. Here, we see the NMR spectrum of 1,2-trichloroethane. Notice how the hydrogens do not appear as single peaks but as a triplet and a doublet. This splitting is due to spin-spin interactions and follows the N+1 rule. The N+1 rule is a key principle in understanding spin-spin splitting in NMR spectroscopy. In the NMR spectrum of 1,2-trichloroethane, the multiplets arise from the interaction with neighboring hydrogens. This interaction is what causes the splitting patterns we observe. The splitting of a hydrogen's peak depends on the number of neighboring hydrogens. For example, a hydrogen with two neighbors will split into a triplet, while one with a single neighbor will split into a doublet. There are exceptions to the N+1 rule. Protons that are equivalent by symmetry or in the same group usually do not split one another. The N+1 rule mainly applies to protons in aliphatic chains or saturated rings. It does not apply in the same way to protons on double bonds or benzene rings. Now, let's look at some common splitting patterns observed in NMR spectroscopy. Here are some typical splitting patterns you might encounter, such as those for XCH-CHY and CH3-CH2 groups. Next, we'll examine some example spectra that exhibit splitting. This is the NMR spectrum of bromoethane. Notice the splitting patterns that arise from the interactions of the hydrogens. Here, we see the NMR spectrum of 2-nitropropane. Higher multiplets can sometimes be difficult to distinguish as they blend into the baseline. This is the NMR spectrum of acetaldehyde. Observe the distinct splitting patterns present in the spectrum. The intensities of multiplet peaks can be understood using Pascal's triangle, which shows the relative intensities of each peak in a multiplet. Pascal's triangle helps us understand the relative intensities of peaks in multiplets, from singlets to octets. Let's explore how spin-spin splitting occurs at a molecular level. The chemical shift of a proton is influenced by the spin of its neighboring protons. This interaction causes the observed splitting in the NMR spectrum. The resonance positions of a hydrogen are affected by the possible spins of its neighbor, leading to splitting patterns such as doublets and triplets. Depending on the number of neighboring hydrogens, a hydrogen can split into different patterns, such as doublets or triplets. In NMR spectroscopy, spin arrangements can reveal important information about molecular structure. For instance, a carbon with 3 neighboring hydrogens will show a quartet, while a carbon with 2 neighboring hydrogens will show a triplet. Next, let's delve into the concept of the coupling constant. The coupling constant, denoted as J, is the distance between the peaks in a multiplet. It measures the interaction between sets of hydrogens, providing insights into molecular structure. Coupling constants remain constant across different field strengths. However, the separation between peaks increases with higher field strengths, while the shift depends on the field. When comparing spectra at different field strengths, note that the 200 MHz spectrum shows compressed multiplets compared to the 100 MHz spectrum, due to the wider scale. Higher field instruments simplify spectra, separate overlapping multiplets, and minimize second-order effects, making them valuable for detailed analysis. Coupling constants are often between hydrogens on adjacent carbons, known as vicinal coupling. Geminal coupling occurs between hydrogens on the same carbon, often with a value of 0. Long-range couplings, such as 4J, occur in special situations, like when hydrogens adopt a specific conformation. These couplings provide additional structural information. Representative coupling constants vary based on the molecular structure and the type of coupling, offering a range of values for different configurations. Couplings beyond 3 bonds are termed long-range couplings and are usually small or non-existent, providing further structural details. Let's summarize the key points we've covered. NMR spectra provide various types of information, including peak types, chemical shifts, integrals, spin-spin splitting, and coupling constants, all of which help determine molecular structure. Spectroscopy, with data from empirical formulas, infrared spectra, and NMR spectra, allows chemists to deduce the complete structure of unknown molecules. Each technique in spectroscopy yields valuable data. Formulas give atom counts, infrared spectra reveal bond types, and NMR spectra show hydrogen environments and relative numbers. With this, we've reached the end of Chapter 3 on NMR. I look forward to seeing you in Chapter 4, where we'll continue our studies. Take care, and goodbye.